On section 1.2, we're going to be talking about functions and a little bit more about graphs. The definition of a function is on page 75 of your textbook, and it's stated as a function is a correspondence, which is a relationship between a first set, sometimes called the domain, we've usually called it just the x values, and a second set, which is called the range, or we've been calling it the y values, such that each member of the domain corresponds to exactly one member of the range. So, simply stated, it means that for every x, there's only one value of y that it corresponds to. Example of something that's a function is if the domain is a student, so the x values are students, and the range are the miles that you're away from Baker, let's say, then Ray is 10 miles, Carol is 5 miles, etc. So that just means that Ray will not be 10 miles from Baker and 20 miles from Baker. He is only associated with one distance of the value from Baker. Example 1a in your textbook on page 1 of the lecture notes is a function because every value that's over there in the left-hand column has only one arrow pointing to something in the second column. We see that 36 is pointed to by two different numbers, but that's okay. Each x has one and only one y value. There can be y values that are duplicates, but each x can only have one arrow going from the left to the right. On page 2 is an example of something that's not a function. The domain is a student like myself, and the range is the schools I've attended. So I have more than one arrow going from my name to schools that I've attended. This is an example of something that's not a function because it has to have only one arrow going from me to the schools that I've attended. Lightning is an example of something that's a function. When you see a lightning bolt, the speed of light is faster than the speed of sound. So if x is the time in seconds until you hear it after you've seen it, then let's take a look at the column x and the 5. If it takes you 5 seconds before you hear the thunder, then the lightning bolt was 1 mile away. If you count 10 seconds, then the lightning bolt was 2 miles away. If you count 15 seconds, the lightning bolt was 3 miles away. If you hear it and see it at the same time, that's not good. That means that it's right on top of you at 0, 0. If you hear only 1 second, then if it's 1 second before you hear it, then that means the lightning is 1/5 of a mile away. So this correspondence can also be graphed in the picture down below using those ordered pairs, and it graphs as a linear function. The time in seconds is on the y-axis and the distance that the lightning away is in miles. But essentially from the chart we can see that for every value of x there's only one value of y. So no matter how long you count, that lightning has to be that exact distance away because that's the relationship between the speed of sound and the speed of light. Here are a couple more examples from your textbook. Example 3, page 77, is not a function because there are two arrows that go from the 9. They go to -5 and 5, so that one's not a function. Figure 2 down at the bottom is a function because you only see one arrow going from the left-hand column to the right-hand column. On page 4 of the lecture notes, figure 3 is a function. We see that 3 x values point to the same value of y. That's okay. X values can use the same y values. There's still only one arrow from each x value going to the y column. The easiest way to tell whether something is really a function or not is actually to use what's called the vertical line test. And if it's possible for any vertical line to cross a graph more than once, then the graph is not the graph of a function. So the key is the line has to be vertical. So we could take a ruler or a piece of paper and slide it across any picture, and it has to be vertical as it goes across. The picture that we have graphed here is the picture of a box, the line in blue, and it would not be an example of something that is a function because as we slide our piece of paper across there, it would touch it at 2 places at one time. So we would slide it across to where it's parallel to that y-axis would be what a vertical test would be. On page 80 of your textbooks are several examples of things that are functions and not functions. If you look at that picture, the ones where it has the lines that cut it in more than one place, as in B, C, and D, are not functions. A, E, and F are functions. So you may want to pause the video to look at those examples in your textbook a little bit more and understand the vertical line test. One of the most important parts of this section is on something called functional notation. If we have an equation like y is equal to x plus 1, if x is equal to 1, we can go through and solve it, and we find y has to be equal to 2. We have an ordered pair 1, 2. If x is equal to 2, then y has to be equal to 3. We have an ordered pair 2, 3. If x is equal to negative 2, y is equal to negative 1. We have a third ordered pair of negative 2, negative 1. Instead of writing y is equal to x plus 1, another way to write it is by writing it in functional notation, which looks like f in a parentheses and an x and close parentheses is equal to x plus 1. F is called the name of the function, and the way that it is read, the f, the parentheses, and x, is read f of x or f at x or the value of f at x. I usually just say f of x when I'm referring to it. It does not mean f times x. F is the name of the function and x is the value that we're using. So the equation that we had above, instead of saying y is equal to x plus 1, we can now say f of x is equal to x plus 1. So we have f of 1 is equal to 2. X is equal to 1 and the value of y is equal to 2. F of 2 is equal to 3 because when x is equal to 2, the value in that parentheses there, y is equal to 3. F of negative 2 is equal to negative 1 because when x is equal to negative 2, y is equal to 1. So what I'd like you to do then is calculate f of 5. So that means you're going to let x equal to 5 and then figure out what y has to be, and then secondly calculate f of negative 6. So you can pause the video and try those problems. You should have gotten answers for A of 6 and B of negative 5. The values of x are the input and the results of it are, which is the same as y, are called the output. The next example that we're going to do is also in your textbook, and the function this time is 2x to the second minus x plus 3. Remember, as we look at this, we have multiplication and we have exponents. The 2 and the x to the second are multiplied, and if we remember our order of operations, please excuse, so the exponent comes before multiplication and division. So that means that you're going to do x to the second power before you do anything with the 2 that's in front. If we wanted to find f of 0, what we're going to do is we replace 0 every place there's an x, and then solving it using the rules for the order of operations. So on our first line there where I have the question marks, that's where we're going to put the value of x. If x is a 0, then we replace all of those question marks by zeros, go through and solve it. We have 0 minus 0 plus 3, f of 0 was equal to 3. I'd like you to pause the video and do the same thing. Find f of negative 1 and f of 3. That means you're going to put that x is equal to negative 1. You're going to put the negative 1 every place where there's an x and solve it. And then on b, you're going to replace the x by a 3 and then solve that. So pause the video and then we'll take a look at the answers. Hopefully you got these answers okay. So here's an example of what we're talking about. Minus 1 to the second is more important because it's exponents than multiplying it by the 2. So negative 1 times negative 1 gives us positive 1, and then we work through the rest of it. On B, we have 3 to the second. 3 times 3 is 9, so we have to do the exponent before we do the multiplication. The real reason that functional notation is used is it's basically a shortcut. If we have two equations and two equation sets, equation set A with equation 1 and equation 2, and equation set B where equation 1 was f of x and 2 was g of x, it's much faster to say that find f of 2 and g of 3, and you would know that you would go to this equation for f and this equation for g. And the other way, you would have to complete this whole statement.